Welcome to pre-lecture 16. We're going to be talking about the matrix exponential today. So remember when we talked in class last time, we talked about the fact that if a matrix A is diagonalizable, then the general solution of this ODE system, linear of course, and homogeneous, will be written as a linear combination of the eigenvectors of the matrix A times e to the eigenvalues of the matrix A, where of course the eigenpair is the eigenvalue lambda sub I with associated eigenvector v sub I. All right, we looked at an example last time where our matrix A was this one here, 7 minus 2, 3, 2, and we found the solution. It was given by this matrix times the initial position vector. So this is a 2 by 2 multiplying a 2 by 1 vector, which results in another 2 by 1 vector. This matrix is serving as a linear transformation on our initial position. Now, the question we have to ask is this matrix playing the role of an exponential, analogous to the exponential solution for a single ODE? But what does that actually mean to calculate the exponential of a matrix? I can recommend this nice video here at 3 Blues 1 Brown. It's about a half hour. If you have time to look at it, it'll give you some nice insights and a perspective that might be slightly different from what we will be looking at in class. Okay, let's go to the next slide. So what even is a matrix exponential? We know what it means when you plug a scalar in to the exponential, when you take e to the scalar. And we also know that the exponential function is analytic and therefore has an infinite series representation that converges. So instead of using e to the z, we can use this infinite sum z to the n over n factorial. In order to make sense of the concept of exponentiating a matrix, then, we can borrow the power series definition, and everywhere we see a scalar in that power series definition, we simply substitute in the matrix. We can do this because matrix multiplication is something that is well defined when our matrix is square. So this is the matrix exponential. We define e to the matrix A to simply be the power series expansion using that same pattern, where now we have plugged in a matrix A instead of a scalar z. Let's think about how we're going to compute this in practice. Let's start with an easy case. Suppose we have a matrix D, which is a diagonal matrix. And I'll use this dot notation to indicate that I've got lambda 1 through lambda n on the diagonal and large zero notation to indicate that I've got zeros on the off diagonal. This is something you should have seen in your linear algebra class as well. So in this case, what does it mean to take e raised to that diagonal matrix? Using the definition that we just looked at, we've got the identity matrix, which is I here, plus the matrix itself, so that's my D, plus, and I'm just going to continue to extend, 1 over 2 factorial D squared. Now, the convenient thing about having a diagonal matrix is when I take the square of that matrix, or D times D, all I have to do is take the square of every element on the diagonal, and nothing else more complicated happens. Similarly, if I'm going to take the cube of that matrix, I have the cube of what's on the diagonal, and nothing more fancy than that is going to happen. So what this gives us when we start adding everything together, put all of these into one large matrix and take, for example, the upper left-hand term in this sum, and we get an upper left-hand term in our sum matrix that itself is an infinite series. We can do the same thing along each diagonal, and the final nth term, the n position, will also be an infinite series, but in terms of lambda n instead of lambda 1. If you're looking at this carefully, you are going to notice that this is the form of the power series for e to the lambda. So each one of these terms, in fact, is the converging series for e to the lambda, the Taylor series. So we can write this in an even more compact form, and we can say that E to the diagonal matrix, in fact, is simply going to be E to every element on that diagonal, with zeros on the off diagonal. So for a diagonal matrix, computing the matrix exponential is quite easy. So this is simply our rule. When we're given a diagonal matrix, the exponential of that matrix is simply calculated by taking the exponential of each of the diagonal entries, and that's it. Now, what if the matrix is not diagonal? Of course, that's our next step, and let's go to the next page. All right, we're now going to look at the case where the matrix A is not a diagonal matrix, but we're going to assume the next best thing. We are going to assume that the matrix A is diagonalizable. Small reminder, a matrix is diagonalizable will mean that it has a full set of linearly independent eigenvectors, and that's an if and only if statement. The statement that is not an if and only if, but that is a helpful check, is if the eigenvalues of the matrix are distinct, then you're guaranteed to have a diagonalizable matrix. So why is it useful to have a diagonalizable matrix? It means that there will exist some invertible matrix that we'll call P, so that when you take the inverse of P, multiply that by A, and then multiply again by P, we're going to turn that into a diagonal matrix. In other words, the matrix A itself can be written as P times a diagonal matrix times P inverse. All right, so now what happens if we take the matrix exponential using the Taylor series expansion definition and we plug in our diagonalizable matrix A? In place of A, we can substitute P, D, P inverse everywhere we see A. And what's going to happen because of this special form is that terms are going to telescope down. Look at this term here, A squared. What do we see? But P inverse P is simply the identity. So we are left now with P, the diagonal matrix squared, times P inverse. So everything is going to collapse because of the P inverse P terms. In other words, P times diagonal matrix D times P inverse raised to the nth power collapses down to P, the diagonal matrix raised to the nth power times P inverse. All right, let's continue with our computation then. Moving to the next equality, we are going to factor out P from the left and P inverse from the right. And what does that give us? That gives us E to the D given by this infinite series term, which of course we know is a fairly simple calculation, and that results in P times a diagonal matrix, which is simply E to the entries lambda 1 through lambda n times P inverse. Now further, if we multiply the matrix A by some scalar t, a very similar calculation is going to show us that E to the AT now becomes P times this diagonal matrix P inverse, where now the entries are not E to the lambda alone, but instead E to the lambda t. Ask yourself the following question. What is E to the A times 0? So in other words, suppose we are starting at time 0. Pause the video and figure out the answer and prove this to yourself. Well, first of all, a matrix A times 0 is going to be 0 itself. So that will result in a 0 matrix. So this gives us E to the 0, where this is the 0 matrix. And my claim is that this is simply the identity. Did you come up with that answer? How would you know that? You know that, again, by using the definition. So in our case, E to the 0 matrix is going to be I plus that matrix, 0, plus that matrix squared over 2 factorial, which is 0 squared, plus, and so forth. So all of those terms are 0 except for the identity. So we have shown fairly easily that E to the 0 matrix is the identity matrix. Okay, let's return to our previous example by going to the next slide. First of all, from the previous page, we have this formula, which I've written at the top here, so we have it to refer to. Now, this previous example is the one that we did in our last lecture. If the goal is to find the solution to the ODE system using the matrix exponential, then what we're going to want to do is rewrite this system as a matrix vector system. So in this case, A is the same matrix of constants that we had from lecture 15. And
the matrix of eigenvectors P
is given by -2, 1, -3, 1. I hope that you all remember how to take the inverse of a 2 by 2. So that will give us our P inverse. And finally, our diagonal matrix is 4, 0, 0, 5. Let's just write down then from our formula what the solution e to the at is going to be. At this point, it's just a matter of some computations. I would challenge you to pause the video and work out the computations yourself, and then come back and see if we got the same thing. If you check back with what we got during our last lecture, this is exactly the solution
matrix
we got before, but this time we're getting it with a slightly different approach. So remember, as a general rule, I have found e to the at, but what is the solution to my ODE going to be? My solution to the ODE is going to be that e to the at that I found, but it is multiplied by my initial state vector, because I am transforming my initial state using my matrix exponential. This matrix vector product then results in another vector, which is my solution. I want to point out that e to the at is not the same as exponentiating each element of at. It is not going to work unless your matrix is a diagonal matrix. And here's an example.
To exponentiate this matrix
that we just worked with is not the same thing as simply exponentiating each term. So do keep that in mind. Let's go to the next page and just do one more example, this time with complex eigenvalues. All right, here we have the same formula as before, just for reference. And this time I'm going to look at a problem that is based on your homework 8 problem number 3. Let's solve this system using the matrix exponential as well, given general initial conditions x1 at time 0 and x2 at time 0. So this system here
can be written in matrix vector format,
where a is given by the coefficients -1, -4, 1, -1. And
the matrix of eigenvectors P contains
complex entries, and therefore so does P inverse. Our diagonal matrix
of associated eigenvalues
also has complex entries. The process for solving this problem is exactly the same. You just have to be careful to keep your complex numbers straight. So pause the video and work through this process yourself, and let's meet on the other side and make sure that we get the same answer.
Notice that we have been able to write our solution matrix e to the at in terms of exponentials and sines and cosines, so the entire matrix now has real entries.
Where did that come from? Well, remember that we have this Euler's formula where e to the it is cosine t plus I sine t. And so taking the terms from our matrix, we can collapse these quite easily. So converting all of the e to the -1 plus 2it terms into e to the minus t times cosine 2t plus I sine 2t, and converting all the e to the -1 minus 2it terms into e to the minus t times quantity cosine 2t minus I sine 2t allows us to collapse this matrix into something much cleaner. Now, since we have our matrix e to the at, we can simply say that our solution is e to the at times our initial state vector. Alternately, you can list the elements of the solution x1 and x2. And these individual terms simply come from multiplying the matrix through times our initial state vector. Let's go to the next page to look at the summary of what we've done. All right, in order to find the solution to some n-dimensional first order linear homogeneous initial value problem, we can see an analogy between the ODE in R, the reals, and the ODE in Rn, higher dimensions. So in the reals, we would have a system that looks like the derivative of our unknown
equals some constant a
times the unknown itself, with an initial condition at time 0 given by some scalar x0. In this case, we already know that the solution xt is e to the AT times our initial state x naught. When instead we're looking in higher dimensions in Rn, we are going to have a vector x take its first derivative, and that will be equal to a matrix of scalars times that vector x. The initial state is given by the vector at time 0, which will be a vector of scalars. The solution in this case is the vector e to the AT, the matrix exponential, times our initial state vector. And of course, our matrix e to the AT is defined by the power series expansion for e to the x.
So the particular usefulness of using the matrix exponential is that we immediately get the solution to the ODE in terms of the initial condition x naught. Remember, in the case of a 2 by 2, when we just looked at the general solution, on the other hand, we could write that in terms of a linear combination of the eigenvectors, say v1 and v2, times e to the lambda 1t and e to the lambda 2t. But that's just the general solution. It is not the solution to the initial value problem. Once we implement initial conditions, we would then be able to specifically find C1 and C2. Using the matrix exponential gets us there immediately.
We're going to get a lot more practice in class, so I look forward to seeing you then.